The objective of this exercise is to optimize and validate a design for the end cap on a solar tracking drive designed and built by Utility Scale Solar Inc. of Palo Alto. These trackers are used in large solar power plants to either move mirrors that form a giant parabolic dish to concentrate the sun's power, or simply to track the sun with individual photovoltaic panels or dish Stirling units. These power plants are usually in remote areas with harsh environmental conditions. To overcome the massive wind loads on these drives, they need to generate 135,000 Newton meters of torque. Unlike traditional drives that use gears, this design is hydraulic. The arrays these drives move are very large, about 3 stories tall, and each power plant has thousands of arrays. To give you a sense of scale, the inner diameter of the end cap is 1.1 meters. So if we can reduce the amount of material used in just one of the parts of the drive, the effects on cost and material use can be huge. The prototype and first generation design uses a cylindrical drum with a flat end cap and weighs about 295 kilograms. In this design, stresses are likely to congregate in the corners, while other parts of the design don't feel nearly as much stress. We'll try to redesign the parts so that the loads are distributed more effectively, enabling us to reduce the mass. Because this design is basically a pressure vessel, the load would be borne more efficiently and naturally by a hemispherical rather than a flat end plate with sharp corners. A simple example of avoiding corners in nature is a spherical bubble. Using this improved hemispherical shape as the basis of the redesign, we'll try to reshape the material to carry the required loads more evenly and reduce material use. We'll try optimizing the design by reducing the wall thickness and reinforcing it with ribs so it stays strong and doesn't deform too much. We'll test these various options in Autodesk Inventor's stress analysis environment. The first iteration of the redesign had a wall thickness of 15 millimeters, an end cap height of 225 millimeters and 6 ribs. The assembly was created in the weldment design environment, which has unique commands for defining welds. To simplify the model for optimization, we've removed the weld from this assembly. Upon review, a wall thickness of 12 millimeters, an end cap height of 160 millimeters, and 6 ribs was determined to be a better solution. The simulation results show that the von Mises stress, deflection, and safety factor are all within the specifications set by the design team. As you can see in this newer design, these stress concentrations are not as dramatic, and the load is being borne more evenly and efficiently. The mass of the new design is 231 kilograms. This is 22% lighter than the original. Because each dual-axis drive has 3 of these end plates, those material savings add up quickly. Now let's review the workflow in more detail.